Okay, I'm still here. No worries.
There's a. Are you going to go through peace? Mainly no, maybe no. I'm going to go through lecture one and lecture two. Okay. So let me share my screen. So, okay. So our first idea of the day should be continuous maps and homeomorphisms. So if you're not familiar with the terminology, don't get scared. Like, so from s- perspective, like we have two spaces, could be vector space. Everyone here familiar with the terminology vector space or something like that, metric space? Okay, I can see someone who's familiar. What about the others? Then topological space and so on. So it could be anything or could be some set, could be a set. Okay. So vector spaces, metric spaces, topological spaces, yeah, sets. And so we want to define a function f. Okay. Okay. So what do we mean by continuous map? So if we have everyone familiar with this thing, open sets. Like for open sets in real number line, we have intervals, open intervals. We call them open sets. Then for R2, we have balls. Okay, so we have a distance, B of R, x naught, y, such that x naught minus y should be less than some value. So this could be an open set and so on. So we are mapping between open sets to open sets. So if we have an open set, so okay, this is my uh, inputs space and this is my output space. So if we have a map from a set here, set of points, could be finite, could be infinite, to a set of points here. Okay. So we can always define a inverse map. No, not always, but we can always define a pre-image. Okay. So pre-image of f. Sorry, it should be pre-image with respect to f for these sets. Okay, let me name this set U and let me name this set V. So pre-image of V. So if this is an open set and due to this mapping, if I get another open set here, okay, so open set to open set. This is called continuous maps. So any questions? What continuous maps are? So the idea is straightforward. If we have an open set in the it my let me use a different color. If we have an open set in my output space, so the pre-image, so let's say this gets mapped to here. Okay. So this was U. If this U gets mapped to here, which is V, now if I take the pre-image, so this should give me U as well, right? So this U gets mapped to here, V. So if I take the pre-image, then it should give me U back again, right? So if this V, this is an open set, and if I take the pre-image of this set, I get here, and this is also an open set, then I can tell this is a continuous map. A typical example, say in R2, we take R2, X and Y. So we define a function. Mhm. R2 to R1. Okay, so n- okay, someone asked a question like in pre-image, input is V. Yes, in pre-image, input is V. Yeah, you're absolutely correct. So we define a function x comma y equal to x square plus y square. Okay, so if we so let's take interval here. So let's set it to 2 to 3, and this should give me, so this interval I'm considering. So this should give me what? Should give me this. Okay. So I'm very bad at drawing. You can see that. So the red one is x square plus y square equal to 2, and the blue one is x square plus y square equal to 3. So, so we can see that this open interval 2 to 3, that and whose pre-image are is this donut shape. Okay. So our donut shape. Okay. So the way we defined our donut shape, so we are not consider taking the boundaries. So that is why this donut shape is an open set. So this open interval 2 to 3, whose pre-image is this donut shape, and we know that this donut shape is an this 2 to 3 interval is an open set, and this donut shape is also a open set. So if I take the pre-image of this 2 to 3 set, yeah, this is just continuous maps. So in the next thing I'm going to explain. Yeah, yeah, this is just continuous maps. So this if this pre-image of this f with respect to interval 2 to 3 should gives me that donut, and we know both of them are open sets, so that is why we can call it this our function. This is a continuous map. Okay. Then next is homeomorphism. So we were talking about continuous maps between two any sets. So we have some set here, we have another set A, we have another set B, and this set could be vector spaces like our previous example R2 to real number R, could be metric spaces and could be anything. Okay, so we defined a map, we take a set U, have taken a set U, and we are taking another set V here from two different sets, and we are defining a map here. We are calling it as F. Okay, now there is another map that is called the F inverse map. So there's a slight difference between pre-image and inverse map. Okay, so for pre-image there is no restrictions here in the output space, but for inverse map there are some restrictions. Okay, okay. So I cannot define pre-image inverse map for R. So R, I need to set it to R2, and now say we how did we define, how do we know f is continuous? Mm, yeah, but for that case we need to define another interval, right? Like say for that your question is this region also an open set, right? Okay, I'm Rana, let me unmute you. I think that will be easier to ask your question. Rana, you can talk now. Okay, maybe uh, there are some technical issues on his end. Okay. Okay, no problem. So your question is the space inside the red thing. That means the green highlighted space. Is it open space on? Uh, yeah, we can define another interval like 0, 2 interval. So 0, 2 open interval are open. So if I take the pre-image of this, this should this should give me that blue red circle. I should use the color red so that you don't get confused. So now, so this region gets mapped to this interval 0, 2, right? For my function f. So if I take the pre-image f of this interval 0, 2, so I should get back this green highlighted circle, right? Please set the chat visibility to every participant as well. It's useful to see others questioning. Vishal, can you help me in this? Hello? Okay. I, I think it's in the chat. So someone raised hand. Okay. Samuel Ehsan. Samuel Ehsan, so you can talk.
Hello, can you hear
Yeah.
me?
Yeah, you're audible.
Oh, I had a question, but I think it's clear now. It was about like if you have a restriction. Can you go to the second page?
Yeah, this one.
Right. So the inverse map only exists when we have a homeomorphism, right?
We have
Uh,
bijections when we only have bijections, right? Bijective maps.
okay.
So,
So
so
can you define what homeomorphism is?
what? Define what?
The homeomorphism between
Yeah,
two
yeah,
sets.
I'm defining homeomorphism now.
Okay, so thank you.
Then we can choose the interval to cover the entire space function. Uh, yeah, we can choose a given interval, but what if we take an interval like this? Let's say if we take an interval like this, so whose pre-image is actually no. This will lead to some confusion. Say if we take an interval like this, so this gives me a closed set in R2. Okay, pre-image, because in this set, we are not taking the boundaries. Okay, in the open set in R2, we don't consider the boundaries, but for this set, to get a map from F to this set, we need to consider the boundary as well. Okay, so when we are considering the boundary, we need to like actually this thing the all everything depends on the topology that we define on the set, but I'm not getting into the details of topology. So y- the question you are asking mainly comes from the topology construction of a set of a space. So maybe after today's class you can hang around a bit. Maybe we can talk a little bit about the topology thing stuffs. But for now on, differentiate. Oh, yeah. That's a good question. Like, what type of restrictions differentiate pre-image and inverse function? So, if you look at the previous example, I was using the terminology pre-image, not inverse. Okay. So, but now I'm using the word inverse. So that's a very good question. Like how do we know when do we say like it's a pre-image or it's a inverse function? So I think I already answered the question that the answer is like if this map F is bijective. If this map is bijective, then we can define an inverse map. Then inverse map exists. Okay. Okay. So yeah. So let me continue defining stuffs because oh, bijective means surjective and injective. Bijective, surjective, and injective. Or we can say one function and one-to function. On-to function. Surjective means on-to, injective means one. Okay. Is that answer okay with you? Okay. Uh, Let me proceed then. Uh, so, like we have defined a map that is f, and we are stating that it's invertible. That means f inverse is the inverse function. I do not know what is injective and surjective is. Okay. So I think for a quick refresher of injectivity and surjectivity should be like we have a domain set and we have a codomain set. Are you familiar with this terminology? Domain and codomain. And we are defining a function between codomain and codomain. Host kindly leave. Ah, okay. So that's a bit tricky. So, do you are you familiar with functions and other stuff? Like, say you have a set and then you define a relation between we take the Cartesian product and then you define the relation between the Cartesian elements of the Cartesian components of the Cartesian product, and then finally you define function. Are you familiar with this construction? Yeah. That okay. So now what you have is so we have a set. Let's take a set X and we have a set Y. Okay. And then we construct a Cartesian product between X and Y. And then we set a relation between, like they could be X1, Y1, X1, comma, Y2, then x2 comma y1 dot 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 x3 comma y1 dot dot dot. You're familiar with this thing, right? You're familiar with this construction. So like then we set some constraint like x1 should x of I should be equal to y of I, something like that. If we set such constraint, then not everything exists like this. We are taking a subset of this entire thing. Then another term should be, so after setting this constraint, we have x1, y1, x2, y2, x3, xn, yn, and so on, so on. Okay. So if we set a constraint like this such that this thing is not unique, the first element is unique, then we call what we call that thing a function, right? So the first elements, if we take the set of the first elements, x1, x2, x3, xn, and so on, this set is called the domain. Okay. And if we take the set of the second element, y1, y2, y3, what we call it codomain, right? Yeah. So, okay. Now we can, so through function, like say our relation here, oh, sorry for the, where was I? Yeah. Sorry for the technical difficulty. So we are mapping it between a set domain to codomain. And then finally, this map. So for our case, the map was when xi equal to yi. Okay. So, okay. So now for each element here, we get an element here. Okay. There could be cases like for this element, I am getting this element. For this element, it's getting mapped to this element also. One liner about the math seems intuitive. Yeah, because I know the math seems intuitive from your end, but some of the students here are asking questions about this things. So that's why I'm answering it. Mainly, mainly the today's purpose is going to be give you the mathematical machinery so that you can do analysis on manifolds and other stuff, which are crucial for GR. Okay. Okay, so there could be cases when this two different point gets mapped to a same point. So in that case, this is not 1, 1. Okay, so in another examples, like domain code, 1, 1 means not injective. Codomain, and then we have a map from here to here. So there could be cases for this entire set, a portion of this set is getting mapped for another function g. So in this case, this is not onto or also not surjective. Okay. So in order to be inverse function to exist, we need both of these property. So each element from he domain should get mapped to each element for codomain. Each element should get mapped to, and this mapping should cover this entire codomain space. Okay, I hope that answers your question about injectivity and surjectivity. Okay. So, Okay, switching gears, like we are nowhere near the things topics I plan to cover today. So switching gears to homeomorphism. So I have two sets. I'm doing a mapping F set A set B, and then I define an inverse map F inverse. And then finally, we know when this is continuous. When this is continuous, if I take a set here, so should give me a set here. So with this set is V, this set is U. And if I take the pre-image, for this case, the inverse map, so inverse map should give me a set here, which is, okay, so inverse map should give me this set here. Okay, actually, it should give me a subset of U, but yeah, for the sake of simplicity, I'm just considering that this should give me the entire U set. Okay, so we know when if this map is continuous. So if the inverse map pre-image of this thing of F of V should give me U. And also for the inverse map, like I have a map from this set to my input space, to my prior space. So for here, if we take an open set here, let's name it as W. So if we take the pre-image of this W set, X. So pre-image of F inverse for W should give me X. So if this is true, that means it is continuous in both ways. That means F is continuous, F inverse is continuous. Then we say F is a homeomorphism between set A and set B. Okay, I hope you're okay with the definitions and other stuff. So now we know what homeomorphisms are. Now we can actually jump into the main topics that are manifolds. So manifolds are what? So I'm not going to define the definitions. I will just draw some diagrams, and and I will just motivate you that this works, and then so on. So so we take a funky looking geometry, and for a point, let's name it as M, set of points. Okay. So for this point here, P, locally this point looks like Rn. So so we can define a homeomorphism between this shaded region to Rn. Okay, through this map, through this. Okay, so definitions of manifold are usually somewhat a bit tedious from mathematician point of view, but for physicist point of view, we just need only one thing and one thing mainly, a space or a set of points that looks like Rn locally. That's why I think Professor Nabil Iqbal and Dr. Nafis Ishtiaq also mentioned that is why Flat Earth Society exists because, like, say, our sphere is a manifold. So, look, if we take a point in that vicinity of that point, there is a region that looks like R2. That's why there are flat Earth societies. Okay. So So if you consider it, we are mapping this yellow shaded region through a map called phi. Okay. So this map is known as what? So we label this yellow shaded region as U. Okay. So for our manifold, this U along with this uh, map phi is known as a chart. Okay. So this thing is called a chart. Okay. Next is So for a given manifold, we can have multiple, many charts. Okay, so let's take the example of spheres. So for sphere, we can say, let's map it to the upper hemisphere. Uh, we have a chart that looks like this. Why didn't the color change? Okay, so we can have another chart. Yes, yes. Okay, let's just use a different color. And so on. So if you take a look at the map of the world, you will see like there are two maps. One for the upper hemisphere. If you Google a flat map of upper hemisphere and another part for the lower hemisphere. If you take a look at any geography book, you will see the map of the globe, map of our globe is divided into two parts. Okay. So this is the reason why, because you cannot cover any R2 space. You cannot cover this entire sphere with one single R2 space. You need two. Okay. So we can actually take many more charts. Like say, I define one type of chart this way. Uh, you- I can define another set of charts on the upper hemisphere going diagonally. Okay. So I think I should use two globes. Uh, I draw the same thing. How should I draw it? Yeah. So you can see I'm covering it with two different type of coordinates. One is like oriented this way and this way. Another is oriented this way and this way. Okay. So there are slight differences. The upper hemisphere, I'm covering it in two different ways. Okay. So you can cover it in many, many, many ways. Like we can also take this divided into this. We can define a chart into this portion as well. And then we can divide the globe into these four parts, then chart here, and then another chart for this part, and finally a chart for here. So we can define many, 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 many charts on our given manifolds. But w- what I am most curious about is the fact that if I take a chart, say this chart, let's take it again. Okay. So chart means this, I'm setting it to U. I'm So this blue bordered region is my U, and then I have a map phi, and this takes me to what? R2. So that's why I stated that if I take a point on this globe that looks locally like R2. So this phi map is taking me to R2 space, right? So so this entire shaded region here with respect to this phi map here should give me a region here in my Euclidean space, right? So let's consider a point here. So with respect to this phi map, this should be mapped here. So I'm setting it to P. So phi of P. So, but this is a Cartesian space, right? So we have X components and Y components, right? In Cartesian space, we have X components and Y components. So we can just use projections here. So we after this phi map, if we take a projection in the first coordinate, okay, this should give me the coordinate of this point, x coordinate of this point. And if I take a projection with respect to the y coordinate, this should give me the y component of this point. Okay, so if you think about it, we don't have a coordinate system here, but we are using this map to define a coordinate system in our manifold. Okay, obviously the coordinate system is local. Now, so if you consider these lines, okay, so these maps are actually these lines, the X part. Okay, let me use these lines are actually these. Okay, so if we take up this point P here, and if we map it, should give me what? The X component. X component only. Ah. So this actually is a real number. And also, if we take the Y thing and then should give me the y component only. That is also just a real number. So if we define our chart map like this way, sorry, phi of p, x of p, y of p. So we are calling this map, we are calling this chart coordinate chart. Oh, oops. Coordinate charts. Okay. So this allows me to define a coordinate system on my manifold M. Okay, now I have a coordinate system in my manifold. Okay. And this x of p and y of p are coordinate functions. Okay. Someone asked a question. When we define charge, do we know? Uh, no, that's a very good question. When we define charge, do we know we are on a sphere or not? So we don't know because for sphere, if we know that we are in a sphere, then we need to know the curvature of the space. Okay, so in order to define curvature, we need the metric, idea of metric, the idea of distance. But in our manifold, we do not have the notion of distance here. So we don't know what is distance. So distance between this point and another point here. We don't know what this is. Okay, this could be anything. Okay, now that we know what coordinate functions are and what charts are, so so I'm taking a funky looking manifold M and I'm defining charts. So in such a way that I want to cover this whole manifold with charts. Another chart here. So, okay, let me just not use V rather than I use U1, U2. That will be handy. U1, U2, U3, and then we have U4, we have U5, and so on, so on, so on. Okay, so I want to cover my entire manifold with charts. Okay, so for each chart, we have a map. Like say mm, for U1, we have map phi 1. For U2, we have a map phi 2. For U3, we have a map phi 3. So phi 1, phi 2, phi 3 takes this to a Euclidean space. Okay. Okay. So this U of i's and phi of i's. So if I take the union of all the i's, this should give me the entire manifold, right? Because we are covering the entire manifold with charts. This is a chart. This is a chart. Can you? We thought, yeah, they are subsets. They are actually open subsets. That's a very good question. Then this is a chart. This is a chart. So for so if I take consider all the charts and then you take a union of all the charts, this should give me my entire manifold. Okay. And for each chart, I have a homeomorphic map to a Euclidean space. Homeomorphic map to a Euclidean space, right? Now there comes the tricky part is, so let's take two charts for simplicity. Let's set it to U1, and corresponding to U1, we have a map that is phi 1, and I take another map chart U2, and corresponding to it, we have phi 2. Then, uh, then do we have some sort of basis for the manifold with respect to the day? Yes, yes. Like, if you consider this thing, this chart, this ideas. Okay. So they form the basis for this local Euclidean space. For this local Euclidean space, they form the basis. Okay. Now let me take my manifold and I have, let's just for simplicity, I'm considering two charts. So this phi 1 takes it to what? To some Euclidean space Rn, and this phi 2 takes it to another Euclidean space, and this should also be Rn. That is actually the very definition of a manifold, that every, like say this map phi 1, phi 2 should take you to the same Euclidean space of same dimensions. Okay. So for phi 1, we cannot have Rm, and for phi 2, we cannot have Rn, where Rm and M and N are not equal. We cannot have that in manifolds. Okay, so for this U1, we can have a set here, and for this case, we can have a set here. Now, we can see we have a shade overlapping region between the two charts, right? So in this overlapping region, so this is actually what? This is actually U1 intersection U2 region. In this region, I can define a map that should take me from, this is phi 1 of U1, and this is phi 2 of U2. So this yellow shaded region should look something around here, and for here, okay. So I can define a map from this yellow shaded region here to another yellow shaded region here that looks something like phi 1 inverse phi 2. Okay. And since this is a homeomorphic map, this is a homeomorphic map, this has to be a homeomorphic map as well. Okay. So this is, okay. So this, all of these are homeomorphic maps. Okay. So if there exists a homeomorphic map like this, from this, in this yellow shaded region, then we can say u of 1, phi of 1, and are compatible charts. To be exact, they are C0 compatible charts. That means there exists this. Okay, let me. 1 minute. Okay. Uh, okay. C0 compatible charts. That means this map is a continuous map, not differentiable map. We don't know what is differentiable maps. Okay. So this is a continuous map. And if you look carefully, we had one coordinate system here, and we are going into another coordinate system with this map. So, so these maps are usually called coordinate change map. Okay, so in tensors, we do what do? We change coordinate systems, right? So in tensors, we need these things actually. So these are the maps that allow me to change between different coordinate systems for tensors. Okay, so s- now let's go back to our case again. So U1, phi 1, U2, phi 2, and then this is phi 1. This gives me a Euclidean here, and this gives me another Euclidean here, pi 2, and we can, in this yellow shape, oh, why?
Riaz, are you not sharing anymore?
I think somehow screen sharing is not working. Oh yeah, I
Okay,
somehow,
it
somewhere
came
my
back on.
screen got disconnected. Okay,
Okay, okay.
yeah, I think I'm sharing now. Okay, so where was I? So I have a manifold. Let me redraw everything again. So I have a manifold here. For this, I have a chart here, another chart here, phi 1, u1, and this is u2, phi 2. Actually, there should be commas there. And for phi 1, we get a Euclidean space, and this looks like here. And for phi 2, we get another Euclidean space. This should map something like here. And in the common shaded region, I said we can def for that common shaded region is something around here, and for this space, the common shaded region is here. I can define a map that is phi 1 inverse, phi 2, and this map is now from one Euclidean space to another Euclidean space. If this map is differentiable map, that means if this is like C1, everyone knows what is C1, C2, C3, right? One-time differentiable functions. And then C2 means two-time differentiable functions, three-time differentiable functions. Then we have C infinity, that means infinite time differentiable functions. So if this map is in for one time, two time, three time, and so on, if it is differentiable, we call phi 1 and u2, phi 2 are C1 if they are if this is if phi 1 is one time differentiable only, then this is a C1 compatible map. Then if this is two-time differentiable, then we have C2 diff compatible map, C3 differentiable, so on, so on. So we can cover our entire manifold with charts which are C1 compatible or only C2 compatible charts. Okay, but they're the subsets. C3 compatible charts and so on, so on. Okay, so now I have to shift the gears a lot. Then I define functions in manifolds. Uh, yeah, you can say that, like that's why m equal to n, but actually that comes from the very definition, like u1 equal to u2 overlap. That's why m equal to n. Actually, this thing actually m equal to n part here that I think you are asking a question. This thing actually depends on the very definition of the manifold. That for any point in my manifold, that should for this point, this point, this point, this point, doesn't matter which point, that should look locally like the same Euclidean space. That's why m equal to n. This comes from the very definition. Yeah, we can take the disjoint sets as well. For disjoint sets, the argument is vacuously true. So that's why I'm not stating that thing. Okay. So we can define functions in our manifold. So what are functions? So so this is my manifold. So I can define function. That means I have a map from this manifold to a real number. No, not all maps has to be C infinity maps, but since we are physicists, we always consider the C infinity maps. There could be some manifolds where we don't need C infinity maps. Okay. Like we don't want to do calculus. So for calculus, it's very useful to do, yeah, only see smooth manifolds. Yeah, exactly. So where were we? So we were defining functions on the manifolds. So function is takes manifold to a real number. So a typical example would be like uh, our Earth, and each point of the Earth we have temperature, right? So in my temperature, I can define this temperature as a function. So that takes any point from this manifold, this temp t function, and gives me a real number, actually positive real number. The questions that are being asked are in the chat. Okay. Okay. So temperature distribution could be a very good example of okay, functions on manifolds. Next, another thing that we have is the curves on manifolds. Curves on manifolds. 1 minute. Curves on manifolds. So curves on manifolds are like what? What is a curve? Say on a real number line, we take an interval and I want to map it. So t, t is a variable from to my manifold. So I should get a curve like here, A to B. Okay, so this lambda, my chat is empty. Uh, I don't know. Why is your chat empty? Did you just recently join? That's why maybe your is empty. Okay. Now this map lambda is taking in a real number value that is from an interval and gives me a point on the manifold. So this curve, let's say a typical example say I start I'm a human, so I live on this planet Earth. So I currently I'm here. Okay, currently I'm here at time t equal to 0, and afterwards I start moving to the north. So so after t equal to t, I should get somewhere around here. So my trajectory from this point to this point is a curve on my manifold, right? Okay. Next is I want to combine these two ideas. These two ideas. I want to combine these two ideas. So how do I combine it? So I have a real number line and I have an interval there and I'm mapping it to my manifold. So I have a curve here on my manifold. And for this given manifold, I define a function. So my function gives me, say for our typical example, I started walking from here and I'm going around here and here, and each point on the curve, I feel the temperature, right? I can feel the temperature. I think the participants can only send messages to the host, and that's why. Oh, yeah. Yeah, that's why. Maybe you can change the participants while asking questions, can change the setting from host to panelist to everyone so that everyone can see the question. Okay. We can't. Uh, okay. I think that's this technical difficulties. I don't know how to resolve this thing. Okay, maybe for each question, I can just pronounce the question so that everyone can get to know what the question is being asked. Okay. Okay. So where were we? So I want to combine these two ideas like functions on manifolds and curves on manifolds. So I have a curve and say this interval. For this interval, I have a trajectory on my manifold. And for each point, say uh, I'm uh, I'm on this earth, so I'm traveling along this curve, and say for each point, I can feel the temperature of the earth. So somewhere I can feel a bit colder, and somewhere it's a bit hot, depending on the geographical locations. Right? Now comes the interesting part. So now comes the interesting part is so I'm moving along a curve. That means this is my curve. So I'm moving around what? Tangents, right? I'm moving along the tangents on this curve, right? So tangents are what? Vectors. So we will need vectors on manifolds. So in a typical Rn, like in a typical Euclidean space, we have a set of coordinate system and so on. So we can easily define a position vector, and then from this position vector we can define. So for this curve we can define a velocity vector and so on. Yeah, because of the construction of the geometry. But for manifold, we don't have a coordinate system, but we have local coordinate system. We define the local coordinate system through charts, if you recall it. Like say for here, this is U1, Y1. So using this local coordinate system, I want to define a vector. Okay. So how do we do that? So for my given curve, a vector is a tangent is a just like Professor Nabil Iqbal said, a vector is a tangent to a curve on a manifold. Okay, so this tangent is my vector. Now, okay, how we need some more information about the vector. We just can't say what this thing is. Okay, so to be more precise, this tangent is actually directional derivatives. Everyone familiar with directional derivatives? Everyone familiar with directional derivatives? So tangents are basically the directional derivatives on M. Okay, I should consider a specific point at P. Okay, so for in manifolds, vectors are defined as rate of change as directional derivatives. They are acting on a function at a given point, say, and for that means we have a real number line A, and this we are mapping it on our manifold M A to B and lambda of t. Now, mm, I've done a mistake. This should be P. So this point here gets mapped to here, and this means this. And this, we don't need this thing. Okay, so this is how we define vectors on manifolds. Okay, vector at a specific point P. Okay, so we are defining vector for this only one point P for this given curve lambda of t. Okay, so grasp the idea. Like for a given curve, the tangent to this curve at a specific point is a vector. Okay, now I want to express this vector with respect to my local coordinate system that I developed through charts. Okay, now I want to express this vector v just like in the Cartesian cases. This vector, position vector, I express it with my x and y components, right? And this I have a tangent vector here. I also express it with my x and y coordinates. Now in manifolds, I define the local coordinate system and I want to express my vector through this local coordinate system. So what is the way to do that? There is one way to do it. There are actually multiple ways, but the way that we use is through the coordinate functions. So if you recall the coordinate functions, so coordinate functions where were they? So this, if you recall this part, so each point gets segmented into x and y components. So these are the coordinate functions. So I want to express my vectors with respect to these coordinate functions. So I can write this derivative with respect to some partials, say x I did a mistake. It should be dx by dt and x plus dy by dt. Not lambda as the curve. Oh, so the idea is not like, so you're taking, your question is why is the f lambda not lambda as the curve representation by the lambda, and we take derivative on the curve. So uh, that's a very good question. Like, I want to express this curve using my this, and I want to see the rate of change of a function. Okay, because derivatives acts on a function. Okay, I guess that's, if that's clear to you. Because lambda is oh yeah, because we need this thing, because we don't know the notion of differentiability and the metric and other stuff for lambda, because lambda function, because lambda are points, lambdas are what? Lambda gives me points on the manifold, right? So in order to do calculus in the manifold, we need a notion of metric, Jiminu. Okay, so but we don't have the metric yet. That's why we can't do calculus on this manifold. Okay, but what we are doing is we are doing a shortcut, I say. That is, the lambda takes in an input from real number, and we have another function that takes it points from manifold to another real number. So if I compose it, so this is actually what? This takes in a real number and gives me another real number. So that's now for real number to real number mapping, we can do calculus. But for real number to manifold mapping, we can't do calculus yet. Okay. Now using the partials, I can write it and they should act. I think I should, yeah. And they should act on my function at a point. Okay. So I have decomposed the Mm, so I have decomposed this directional derivative to partial derivatives. So for this example, I am taking two-dimensional manifolds, right? So manifolds that are homeomorphic to R2. For any typical case, so I'm just using phi t x of phi, and we have the Einstein summation convention, phi equal to 1 to the dimension of the manifold, and they should act on this curve. Okay, so I hope this is clear. Like for this, this example was for uh, R2. Now I'm just converting these ideas to Rn. Okay. Okay, I should give a subscript here P, because we are defining tangent vectors at a point P. So this is not covariant contravariant subscript. Okay, this is like I'm defining a tangent at this point P. That is why I'm using this label P. Next is, so what are these? What are these terms? I can write them simply as V mu. And what are these terms? The other terms. These terms. They are just simply partial derivatives. And they act on So if you look at the entire term, this thing, okay, this thing does not depend on the function here, right? This thing actually, this thing actually comes from what? The tangent derivative, ddt. And this tangent derivatives comes from what? The curve. Okay. So we, our vectors, these are the vectors. This is a vector in the manifold. So what is a vector? In manifolds, vectors take in functions and ma- vec in manifolds, vectors at a point P takes in a function and it should give me a real number. Okay, no question so far. Okay, so we have defined what a vector at a point is. Now we can do the interesting. Okay, S- this was my manifold, this was my curve, and for this lambda curve, I define this lambda curve for this coordinates is, let me just copy this thing and then, yeah, cool. For this same, I defined it for this coordinate system, local coordinate system. Oh, I should be a bit serious about this thing. I didn't cover the entire curve. And then I can define another set of coordinate system. And from chart compatibility, so this is a chart. This is another chart. Okay. From chart compatibility, we know that there exists a map. So this, for this I get another. So from chart compatibility, we know there exists a map from here to here. So, and I also stated that we will use this map to change bases in our change bases. They are known as what coordinate change map and something like that. So now that we have our vector was this arrow, similarly this arrow. Okay. So now I want to define this vector, my vector from this chart, x coordinate charts x mu to another set of coordinate charts that are x mu alpha. Okay. So actually phi 2 is I hope this idea is clear to you, right? So this is x mu 1, x mu 2. This is x alpha bar 1, x alpha bar 2, and so on. So I want to change the coordinate system for my vector. So this vector. So my vector in this coordinate system was v of mu, x of mu. Okay, this is my vector component in x mu coordinate system, and this is my vector basis in x mu coordinate system. Okay, so I want to see how this basis, uh, how do I change from one basis to another for different coordinate systems? How basis change from one coordinate system to another. So basis of u of mu equal to x of mu, and these are for x mu, and this is for x alpha. And we have another vector x alpha bar. Okay, now I want to define a relationship between him and him. So how can I do that? I will just simply use the chain rule. So x mu equal to mm, x of alpha bar, x of mu, and then we have x of alpha bar. Okay, we have the Einstein summation convention, and from this, we know this is equal to E of alpha bar, and then we get, yeah, that is actually, is that the Jacobian? Yeah, that is the Jacobian. Yeah, exactly. Yeah, this thing is called the Jacobian matrix. And this is, so we know how bases convert from one coordinate system to another. Now, what about vector components? So vector components were like v of mu, that was dx mu by dt. Mm, If you look at here, we have labeled it as this, and we are calling it as vector components. So for vector components, I will again use the chain rule, and I will again use the chain rule. Now, what is this? This is actually my vector component for, okay, so this is my vector component in x alpha coordinate system. So that's how vectors between different, from one coordinate system to another transform in a manifold. Okay, so you were familiarized with the transformation rule from one coordinate system to another, but behind the scene there were a lot of mathematics going on. So this is the mathematics. Uh, So next is for my manifold, I defined a curve, and for a single point, I defined this tangent vector. But from this point through this point P in this manifold M, there could be multiple curves, like a curve here, another curve that should go this way, another curve this way, this way. For each curve, I get a tangent, right? For this curve, I get a tangent like this. For this curve, I get a tangent like this, another tangent, let's say like this, and so on. So if I take the linear combination of all these, if I take a combination of all these tangents, so I get a vector space that is known as Tp of M, that is tangent vectors at M through the point P. So this is known as the tangent vector space. I should have tangent vector space at M through the point P. Okay, now in linear algebra, if you're familiar with linear algebra, someone asked a question. Yeah, it's Jacobian. Yeah, I think I answered the question. Okay, so if you're familiar with linear algebra, for a vector space, we have another thing called is covector space. And I think there's another name for this. I forgot. Dual vector space. Yeah. Vector space, covector space, or dual vector space. In linear algebra, we have something like that. So in manifold as well, this Tp of M is a vector space. So there should be a dual of this vector space, right? So dual to Tp of M is known as Tp star of M. This is what? Covector space. This Tp star of M is the covector space for this vector space here, or the dual vector space on this manifold. So now, so since we have a dual vector space or a covector space, that means there exist covectors. So, so what are covectors? Covectors are objects that take in a vector. Okay, similar to like vectors, we are defining vector on a point. So we are defined a vector for this point. We have defined a vector space in the vicinity of the point P. Okay, so similar to the vectors, for covectors as well, we are defining it on the point P. Okay, so we are defining the covectors at the point P, and they should take in vectors at point P. That means the tangents at point P, and they should spit out a real number. Okay, just like in linear algebra. So linear functionals and other stuff. In linear algebra, we have seen the linear functionals and they take in vectors and they spit out a real number. Okay, so mm, so typical example, let's take a covector and let's feed it with a vector. So they should give me what? So if I mm, okay, so if I separate this thing in, write this thing in components, the local with respect to this local charts, components and local charts. So this P is for the point P. Okay, don't get confused with. So this thing should spit out a real number, right? So this thing should give me like what? For this, something like this. Okay. Okay, let me just omit the P part, I think. Oh no, I can't omit it because for vector fields I will need the thing. Okay, what I can do is I can use brackets. Yeah, I think this is okay now. Okay, so covectors at point P takes in vectors and they should, so this is actually a real number. Now we know from one coordinate system to another how this thing transforms. Okay, so we want to know how covectors transform from one coordinate system to another coordinate system. So, mm, uh, yeah, I think someone raised the hand. Okay, I think, okay, so for simplicity, I'm just omitting the P thing. So this is a real number. They should be equal to this thing because fro- from coordinate system to another, these real numbers or scalars don't change, right? So that's why they should be equal. Now I want to express this thing with terms of V of alpha. So we have already done that, and that is exactly this thing. So I will just copy this thing there. I'm not wrong. That's just X of alpha bar. Yeah. Mm, okay. So now equating both sides, this and this, component by component, I get alpha equal to n of mu, x of mu, x of mu alpha, and then x mu. So this. So this is how covectors transform from one coordinate system to another. So one local coordinate chart to another local coordinate chart. That's how they transform. Okay. Now we can define a thing called a gradient. So gradient. So on manifold, we are defining a smooth function f, right? That takes me to a real number. Okay, so a gradient of a smooth function. So I'm taking a gradient of this function should take in what? It takes in a vector. So vectors come from curves and again at point P. So gradient of this function at point P. Okay, so at point P, I should write it, should take in a vector and this should give me a real number. Okay, so what this thing does so this is what? Directional derivatives, that means ddt of t, and if I act the gradient operator through it, this should give me rate of change of this function at lambda of t equal to p. So I'm taking a gradient of this function f. This should give me this directional derivatives of this function. I think I should write it as f. Okay, so this thing gives me directional derivatives of this function actually. Okay, now we can actually say take. So now let's take f is an arbitrary function that takes in one point from my manifold, say the point P, and spits out a real number. So if you recall properly, the coordinate charts are also somewhat something like that. So they take in are where are they? Where are they? Where are they? Where are they? Uh, they're here. Okay. So coordinate charts also do what? They're not here. Yeah. So these things also take a point from the manifold, and this thing gives me one component, the x component. This function gives me only the y component. So they are also taking points from the manifold M and spitting out a real number. So we can replace our uh, function with a coordinate function, and then we define a gradient of that. So they should take a vector, and if I decompose my vector in my coordinate chart, I should use mu. So if I decompose, okay, so x mu. Okay, now for a given point tangent, these vector components are constant. For a given coordinate system, these vector components are constant. Okay, so and this is a so they think they just come outside. Oh shit! I should have used mu. No. Where did the emu go? This page? You mean this page? You mean the covector page, right? Here. Oh yeah. So we didn't from our construction we didn't need any emus and other stuff. Okay. We just know that scalars don't change from one coordinate system to another. They're just the same point, just different representations. Okay. So we just use that thing for the equality and then just transform the coordinate system for the vector components. And through that, we defined how covectors transform. Okay. We didn't use any sets of coordinates for covectors. I hope that answers your question. Okay, very well. And then finally, we have now this. Oh, I I I did the mistake again. Now is this thing acting on this thing should give me the direction. So this thing should give me a Kronecker delta. V mu Kronecker delta nu. Did I do any mistake? Mu. So this thing gives me V of mu. This should be downstairs, this should be upstairs. No. So we can see that this coordinate function, gradient of these coordinate functions that are this, if we act them on the basis, these are actually E mu's, right? If they act on the basis, they give me Kronecker delta. So isn't that the definition of the basis for covectors, right? So covectors bases are actually no. So in the linear algebra, if we take a basis, like say basis for a covector, and if it acts on the basis of the vector space, they should give me a Kronecker delta. So if you look at carefully, this gradient is also giving me the same thing. They are acting on the basis of my coordinate coordinates of the chart, and then they're spitting out a Kronecker delta. So these things are the basis for what? For covector space. Okay, so I can decompose my covector with components and bases. And for bases, and this is for x new, and now I want to change it to another coordinate system, say x. Okay, now to this coordinate system, I can again use the chain rule. Oh. So yeah, using the chain rule, I can see that this is how, again, this is the Jacobian matrix, basis of covectors are transformed from one coordinate system to another. Okay, and this thing can be written as mu plus x mu, and in another coordinate system, now using the above expression, this one, I replace this term with the above expression. Equating components from both sides, I get s- oh, so this is how my covectors transform from one coordinate system to another. Okay, so we know how they transform, like from jargon, like we know like vectors and tensors, and they have certain transformation rule, but we don't know how they come up. So this is how they come up. Okay, okay. Now we have defined the most crucial part. Now let's define what tensors are. Tensors. So let's take a map x comma y, and let's set it equal. And let's take it equal to x times z. Now, if I take it x plus y and z, this should give me x plus y times z. And if I do the distribution law, what are these? These are nothing but, so if you look carefully, I have a linearity in this term. Similarly, I can show we have linearity in this term as component as well, part. Okay, for this function. So if we have linearities like this, we call such maps bilinear map. Okay. Okay. Now, now we have bilinear maps. Similarly, x1, x2, dot, 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 x of I plus y of I, x of n. For such map, if I can decompose it into like, so this type of maps are known as multilinear maps. Okay, so multilinear maps. So what are tensors? Tensors are multilinear maps with certain rules. With some rules. So what are the rules? Is, say we are familiar with the thing. Let's take sorry. Let's take a R comma Q R comma S tensor. So R comma S tensor should take in R number of covectors and also S number of vectors. And after taking like R number of vectors and S number of R number of covectors and S number of vectors, they should give me a real number. So this is the rule, additional rule. Okay. So let's go through some examples. Say a covector. Covector means 0, 1 tensor. So 0, 1 tensor. So what a covector does, it takes in a vector that is 1, 0 tensor and gives me a real number, right? So next is the metric tensor. Metric tensor takes in two vectors and it should give me a real number. Okay. A 3, 2 tensor should take in three covectors and two vectors and it should give me a real number. That is what tensors are. Now, let's have a tensor p comma q tensor. That means it can take s. That means it can take p number of covectors as input and q number of vectors. And afterwards, it should give me a real number. And another tensor, r comma s, tensor t, this should take in r number of vectors and s number of covectors. Sorry, mistake on my end. And after taking all of this as input, this should give me a real number. Now, if I define an operation like this should take a p plus r number of covectors and s plus q number of uh, I haven't gone through the indices part yet. I will go to the indices part. Wait, hang in 2 minutes. And this thing should give me a real number. Okay, so this operation is called tensor product. I think everyone's familiar with this thing. Tensor product. Now, the thing you are asking for, say, let's take two covectors. Okay, now if I tensor product these two things, this thing takes in vectors and this thing takes in vectors. So tensor product of this thing should take in two vectors. This thing should take two vectors and should give me a real number. So this thing should take two vectors. Mm, And this thing should give me a real number. So how is it? If I write it component wise, now if so I can rewrite this thing like beta, alpha, beta. Okay. And then finally, there I'm acting it with this thing should give me alpha, beta, Kronecker delta, alpha, mu, Kronecker delta, beta, nu. So this is a real number. Okay. Now a tensor like this, I want to know how do they transform. So I want to know how this tensor transforms. I'm almost at the very end of my time, and so I'm just gonna say how n by n tensors transform, and then I'll just wrap up. Okay. I think Michal, are you there? Okay. So Michal is maybe okay. Next is uh, now I want to. They are for alpha beta coordinate system, and I want to write it in say. Yeah. Give me 5 minutes. I will just wrap everything up. mu and new coordinate system. Okay. So I just want to write this thing in mu and new coordinate system. So how can we do that? Just let's express this thing in mu. And then since this is a tensor, okay, this is actually tensor with its tensors with its bases, they are actually equal because components and bases change, but the entire tensor thing does not change. Okay. Now, if I use the transformation laws for this part and this part, okay, I did a mistake. Should be. And then combining everything. Now, if we equate this and this, we have the tensor transformation rule for I guess now you know how this is why we write the certain transformations rule in lecture one. So for a typical tensor, U of R, V1, P2, V of S. So for a typical tensor, what do we mean by, we actually mean the component thing, but there are actually, uh, we don't write the basis part. So they are the basis part. But when we say R comma, this is a R comma S tensor, we actually consider we actually mean the component part, but we don't write the basis part. So if you look carefully, this thing, there there are R number of covectors that can act on this part, and there are, it should be S number of vectors on which they act on. Okay. So, and we have seen it from the above example. I can actually give you more examples, but I'm running short on time. So I will just quickly wrap up everything up and just for each covector. So I will just want to write the transformation rule. Mm. Of R x of mu of R. These parts are for the uh, vector part, the upstairs indices, and for the lower stairs indices, we have Okay. Beta 1. And so on. So that is why in lecture 1 we wrote it that way. Okay. So that is how the transformations rule are here. I have shown you one explicit example. You can just do it for the rest of the cases. Similar treatment. Okay. But if you think about it, up to now, we have only considered vectors and tensors for a point P. So my vector V tensor was defined for point P. But I want to define it for every point. In my manifold, I want to define it. So what do I do? My vectors at point P should take in some real functions and gives me. So what if I just relabel this thing, like I have a vector that takes in a point from the manifold and a function. And this thing should give me a real line. So just by losing this argument P here and just using it, setting it as an input, I can define vectors for any points. This. Obviously, for these points, there exists another curve. For these points, there are other curves as well. Other curves. So we had vectors at a point in M, or my point was P, to just relabeling this thing, we have vectors for all points in M. So, and this thing are known as vector fields. And similarly for tensors, we have tensor fields. So these things are crucial, like when we are doing covariant derivatives and other stuff, these are crucial ideas. So my next topic was covariant derivative, but I think I have been 7 minutes extra, so I think I should stop right here. Yeah. Michelle, are you there? Michelle's not here. Uh, okay, wait. Yes, I will upload the notes. Okay, so I think I have one topic left, that is covariant derivatives. So covariant derivatives are actually what? So we have manifolds. We are on a manifold, and for a point here we have a tangent vector space. So we have a vector space, and for another point here we have a vector space. Okay, so I want to compare vectors from this space to vectors at this space. But in our Euclidean space, a vector here and a vector here, I can simply compare these two vectors. But for manifolds, I cannot simply do that. Okay, so for that reason, I need to define something. So what is the way to compare vectors here with vectors here? So that thing is called covariant derivatives. Okay, so what covariant derivatives does? Covariant derivative. Okay, so covariant. I want to define covariant derivative for manifold. Let's say I have a function that takes my points from manifold to a real number. So covariant derivative of a scalar function should be exactly like the actual partial derivatives. That means this should behave exactly like the gradient thing. And so what gradient does is it takes in a vector and it gives me a real number. So this is exactly what covariant derivatives should do for functions. Okay. Now for vectors, okay, it should take in a tangent vector at a point P. Yeah, this should take in. Now for vectors, covariant derivative of a vector should take in two arguments. Yeah. So for vectors, the covariant derivative should take in what? A vector field. So I have a manifold. So I want to define a covariant derivative for a vector field. So I have these curves for each curve. I have points for each point. I have a tangent vectors and other stuff. And let me relabel P1, P2, Q1, Q2. And then this thing should take. So V is a vector field and X is another vector field. So just this for these curves, I get a V vector field. For another sets of curves, I get the X vector field. So covariant derivatives of, if I take the covariant derivative for this vector fields, so this thing should take in another vector, another sets of vector fields, another vector fields, and this thing should give me another vector field. So more precisely, let's take a covariant derivative of a vector at point P. So my manifold, this is my curve. For this curve, I have a point P, and this is my vector at point P. And same manifold, another curve, but same point P, and this thing gives me another vector, tangent vector Q. So this thing should take in this vector, and this thing should give me another vector. So ultimately, and takes in this thing and should give me same. Actually, I'm drawing different manifolds, but they are the same M manifold. So another P, and this is the Y of P. Okay, so I hope the picture is intuitively clear to you what this thing is doing, and this thing has some properties, right? Uh, Professor Nafis defined this thing in a different way, but I'm defining it like more mathematically, like this thing should have this properties. So this covariant derivative of a vector field should have properties like g of y. They are linear for these arguments. Okay. Next is they are linear in these arguments as well. Okay. And finally, and then this is called the Leibniz rule. Okay. Now the final holy grail thing. Then I'm showing this. I will just end the today's session. Okay. Let's define a covariant derivative of vector field for this W vector, another vector field. So let's decompose everything. And then if I write this thing with respect to a coordinate system, that is u mu, and W as mu, e mu, and then using the linearity properties, we have v mu, e mu, uh, W mu, e mu, and then using the Leibniz property, this should, oh, I made a mistake. Indices. Okay. And then this thing should add email. Okay. So now this part are just functions. Okay. Coordinate functions. Okay. So when covariant derivatives act on these coordinate functions, they act like what? Partial derivatives. W of mu, E of mu, E of mu, W of mu. And this thing we have an issue. I will just talk about it separately. So this thing actually acts like partial derivatives. So if you recall, this thing means, so this is just differentiating this with respect to this. And finally, and now this problematic thing. So we know this is an operator. Covariant derivative is an operator. And since it's a derivative, that means it's a linear operator, right? So linear operator, so there exists some linear transformation here. So I think in Professor Nafis's lecture, you will find it like he wrote this term in this way. Mu nu sigma E of sigma. So this is how Dr. Nafis wrote it that way. And he said, this is the linear transformation term. So this thing transforms the coordinates. So I can give you a good example of this thing, why this works. Let's say, let's take some polar coordinates. Okay. And let's look at this term. This term was E mu. nu mu. That means if I change a little bit for this basis, what does the change occur in this basis? So for polar coordinates, say my particle was here. So for that case, I have a basis here. That is my radius vector, basis for the radius vector. After a small change, now my radius vector has been shifted to here. Now you can see there's a change for this displacement. Okay, so this essence is being captured through these terms, these linear transformations. Okay, these essence are being captured through this thing, like this example here. It was first along the x-axis, and after some rotation, it's pointing in a different direction now. So the basis vector has changed. So this essence is being captured for any typical odd-looking manifold through this term, or in Dr. Nafis's lecture, through this linear transformation. So he's going to explain in the next lecture, he's going to explain this thing in a bit more detail and give more emphasis on this thing. Okay. So with that, I would like to end my lecture today. I'm sorry for going over time. I think I took 20 minutes more. A bit sorry because I think there are a lot of introductory stuff that has not been defined very well. So I think I had to define them properly. Okay, so any questions on your end? Okay. If not, I think I don't know whether did a very good job in explaining this thing or not. Yeah, go ahead. You can let me just unmute you. I think that will be helpful. Any resources? Yeah, actually, there are a lot of resources. First of all, I took help from the Anatomy of Geometry that's actually given by Frederick Schuller. Everybody knows him. And some part of General Relativity lecture notes of Harvey Real. Okay. You will find resources like this from these two from the PDFs. They are available in the online. You can just Google search Anatomy of Geometry, Frederick Schuller, and also okay, sure. Actually, I don't know how to change that, or else I would have changed that. Yeah, yeah, yeah. I have the PDFs, though they are highlighted and written, so I just have to re-download them and I can upload the. Yeah, you know about the Schuler. Secondly, where are all the homeworks uploaded or submitted? Actually, homeworks are not officially been set, but if you follow the lectures, like Professor Nabil stated that this should be a very good example for exercise, I think they will be your homework. So if you take the class notes properly, or you can revisit the recordings of the lecture, you may find the homeworks. More to that later, maybe. Official LaTeX homework will be posted in the Slack, I hope. Okay. So, will there be any exam? No, I don't think there's gonna be an exam. I think your evaluation will be based on your attendance and homework, nothing else. Okay. So I'll just end the meeting here. Okay. You have a lecture tomorrow, I guess. So more to covariant derivatives on the lecture. So don't miss it. Okay. Just the lecture from where we will learn. Yeah, you will be provided with exercises, a lot of exercises. Don't worry. Just wait for the exercises. Okay. I'll catch you guys maybe some other time.
Okay, thank you, Riyaz.
Okay. Sorry for a bit going over time.
No, don't worry, don't worry.
Okay. Okay.
Okay,
Okay. Bye bye then.
I'll end the webinar.
Okay.